Good afternoon, everyone. I am fine. How are you? I hope you will be fine. Welcome back in my channel, Dr.Satendra Kumar. Dear friends, if you want this type of videos related to mathematics for higher level, then you need to subscribe, share, and like my videos and my channel. Today, we will discuss inner product space of two vectors and more vectors. Now first inner product of two vectors. Inner product of two vectors. Inner product of two vectors. Let VF be a vector space where F is real or complex field and alpha comma beta belongs to F and x comma y comma z belongs to VF, then bracket comma bracket close is called inner product. Inner product. If number first x comma y, x inner product y always belongs to F. Number second, alpha into x plus beta into y inner product z equal alpha into inner product x with z plus beta inner product y with z. Now third property, xy inner product equal to y x inner product, and this is the in real field. Now field is complex, then inner product of xy equal to inner product of yx complex conjugate. Now fourth property, the inner product of xx always greater or equal to 0 and inner product of xx equal to 0 if and only if x equal to 0. Okay. Now repeat the inner product of two vectors. Let F be a vector space where F is a real or complex field and alpha comma beta belongs to field and x comma y belongs to vector space element. Then simple bracket comma bracket close is called inner product if inner product of xy always is element of field. Number second, alpha x plus beta y inner product with z equal to alpha inner product of x with z plus beta inner product of y with z. This is the linearity property. Now third, conjugation, inner product of xy equal to yx and xy is equal to yx bar. Number fourth, the inner product of x with x always greater or equal to 0 and if inner product of x with x equal to 0 if and only if x is equal to 0. Now next, usual or standard inner product of two vectors. Usual and standard inner product of two vectors. Usual and standard inner product of two vectors. let x equal to x1 comma x2 comma up to dot xn, y is equal to y1 y2 up to dot yn be two vectors, then usual inner product of x and y for V and R is given by x inner product with y is equal to x1 into y1 plus x2 into y2 plus up to dot xn into yn. Okay, this is equal to written as summation I is equal to 1 to n xi into yi. Okay, and usual inner product of x and y for VNC is given by x inner product with y is equal to x1 into y1 bar plus x2 into y2 bar up to dot plus xn into yn bar. This is equal to summation I is equal to 1 to n xi into yi bar. Now, what is inner product space? Now we define inner product space. Now the definition of inner product space: let VF a vector space. Let VF is a vector space, then VF inner product VF comma bracket inner product bracket close is called an inner product space. An inner product space if number first linearity in linearity alpha into x plus beta into y inner product with vector z is equal to alpha into x inner product with z plus beta into y inner product with z. Number 2, conjugate symmetry. In this case, x inner product with y is equal to y inner product with x and x inner product with y is equal to y inner product with x bar. Number 3, inner product of x with x always greater or equal to 0 and inner product with x is equal to 0 if and only if x is equal to 0. Okay. Now there are some problem. Now problem number first. Let u equal a1 comma a2 and V equal B1 comma B2 belongs to V2C and IP, that is inner product, is defined U inner product V is equal to A1 into B1 bar plus A2 into B2 bar. Then so that V2C be inner product space, IPS, that is inner product space. Now repeat the problem. U equal to A1 A2 and V equal to B1 B2 are two vectors, element of V2C, and their inner product is defined as U inner product with V is equal to A1 into B1 bar plus A2 into B2 bar. Then so that V2C will be inner product space. Okay. Now let U equal to A1 A2, V is equal to B1 B2 are two vectors. Similarly, W is equal to C1 C2 belong to V2C and alpha comma beta belongs to C, that is element of field. Therefore, alpha into U plus beta into V can be written as alpha A1 A2 plus beta B1 B2. Okay. Now it can be written as alpha A1 plus beta B1 comma alpha A2 plus beta B2. Now we take linearity. For linearity, we take alpha into U plus beta into V. We can say this is the first property here, linearity. Alpha U plus beta V inner product with W can be written as alpha A1 plus beta B1 into C1 bar plus alpha A2 plus beta B2 into C2 bar. Okay. Now we can write alpha into A1 into C1 bar plus A2 into C2 bar plus beta into B1 C1 bar plus B2 C2 bar. This is equal to alpha U inner product with W plus beta inner product with VW. Okay. Now second property, conjugate symmetry. Take UV is equal to A1 B1 bar plus A2 B2 bar. Now V inner product with U can be written as B1 A1 bar plus B2 A2 bar. Okay. Now V inner product with U conjugate is equal to B1 into A1 plus B2 bar into A2. This is equal to U inner product with B. Imply that U inner product with V is equal to V inner product with U bar. Okay. Third property, U inner product with U is equal to 0, that is A1 square plus A2 square bar is equal to 0, implies A1 is equal to 0 comma a2 is equal to 0. That is u is equal to a1 a2. This will be 0 comma 0 equal to 0. Hence B to C is an inner product space. Okay. Now next problem. Problem number 2. So that VNR be an inner product space under standard inner product defined by U inner product with V equal to A1 into B1 plus A2 into B2 plus up to dot AN into BN, where U is equal to A1 comma A2 up to dot AN and vector V is equal to B1 comma B2 up to dot BN. Okay. Comma for every AI comma BI belongs to R or I equal to 1 comma 2 up to dot N. Now answer. Now repeat the question. We want to show that V and R is an inner product space under the standard inner product defined as U inner product with V is equal to A1 B1 plus A2 B2 up to dot AN BN, where value of A is equal to this and value of B is equal to this. That is, for every AI comma BI belongs to element of field where I is equal to 1 2 3 up to dot N. Now first we show linearity. For linearity, take U is equal to A1 A2 up to dot AN, B is equal to B1 B2 up to dot BN, W is equal to C1 C2 up to dot CN, and alpha comma beta belongs to R. Now take alpha into U plus beta into V is equal to alpha A1 comma A2 up to dot AN plus beta into B1 B2 up to dot BN. Now it can be written as alpha A1 plus beta B1 comma alpha A2 plus beta B2 dot dot alpha AN plus beta BN. Now we take inner product of alpha U plus beta V with W can be written as alpha A1 plus beta B1 into C1 plus alpha A2 plus beta B2 into C2 plus up to dot alpha AN plus beta BN into CN. Okay, that is alpha into A1 C1 plus A2 C2 plus up to dot AN CN plus beta into B1 C1 plus B2 C2 plus up to dot BN CN. This is equal to alpha into U inner product with W plus beta V inner product with W. This is the linearity. Now second property of for IPS, symmetry, conjugate symmetry. Now U inner product with V is equal to A1 into B1 plus A2 into B2 plus up to dot AN into BN. Okay. Now we can write inner product U with V. V with U is equal to B1 into A1 plus B2 into A2 plus up to dot BN into AN. This is equal A1 into B1 plus A2 into B2 plus up to dot AN into BN. That is U inner product with V. Imply U inner product with V is equal to V inner product with U. Now third property, U inner product with U is equal to A1 into A1 plus A2 into A2 plus up to dot AN into AN. That is A1 square plus A2 square plus up to dot AN square. Always greater than or equal to 0. Now if U inner product with U equal to 0, that is A1 square plus A2 square plus up to dot AN square is equal to 0. Imply that A1 is equal to 0, A2 is equal to 0, up to dot AN is equal to 0. Now U equal to A1, A2 dot dot AN, always equal to 0, 0 up to dot 0, that is U is equal to 0. Okay. Hence V and R is an inner product space, IPS, that is inner product space. Now next topic, length or norm of a vector. Now we explain length or norm of a vector. The length or norm of a vector in inner product space. Let VF is an inner product space, and U belongs to VF, then norm of U is denoted by U double line both side and defined as norm of U equal to inner product of U with U whole under root. Let with an example, U is equal to 3, 0, 4 belongs to V3R. Now norm of U is equal to U inner product with U by under root. This is equal to 3 into 3 plus 0 into 0 plus 4 into 4 under root. This is equal to 9 plus 16. This is equal to 5. Okay. Note, inner product of two vector, inner product, that is IP, of two vector is a scalar quantity. is a scalar quantity. So norm is a scalar quantity. So norm is a scalar. Okay. So norm is a scalar. Now again, next topic, orthogonal vector. Orthogonal vector. Let we define the orthogonal vector in inner product space. Let VF is an inner product space. VF is an inner product space and U, V belongs to VF. Then U is said to be, vector U is said to be orthogonal to V if inner product of U with V always 0. When the value of two inner product of two vector always 0, then we can say both vectors are orthogonal to each other. Okay. Since the inner product of V and U is equal to 0, that is we can say here U is orthogonal with respect to V or V is orthogonal with respect to U. Now next definition, orthogonal basis set. Orthogonal basis set. What is orthogonal basis set? Let VF is an inner product space and the set B equal to V1, V2 up to dot Vn is the basis for VF, then it is called orthogonal set if Vi inner product with Vj is equal to 0 for I not equal to j. Okay. Now orthonormal basis set. Orthonormal basis set. Now orthonormal basis set. Let VF is an inner product space and the set B is equal to V1, V2 up to dot Vn is the basis for VF, then it is called orthonormal set. Orthonormal set if inner product of Vi with Vj equal to chronicle delta Ij. This is equal to the value of chronicle delta Ij is equal to 1 over 0. the value of 1 when I is equal to j, or for I is not equal to j, the value of chronicle delta is always 0. Okay, that is orthonormal vector can be written as orthonormal vector equal to orthogonal vector upon norm of orthogonal vector. That is, we can repeat orthonormal basis set that VF is an inner product space and the set B is equal to V1 V2 up to dot Vn is the basis for VF, then it is called orthonormal set if inner product of Vi with Vj equal to chronicle delta Ij, the value of chronicle delta 1 or 0. 1 is when I is equal to j, or when I is not equal to j, then value of chronicle delta always 0. Now we have orthonormal vector is equal to orthogonal vector upon norm of orthogonal vector. Okay, student, this is